Hi everyone, I'm Yuzhang and I'm a member of the Science Communication Working Group, and we host this exciting workshop series. For the data visualization workshop this year, I'm happy to introduce Professor s.braun, a visiting assistant professor in the College of Arts, Media and Design at Northeastern. There, he teaches courses in data visualization and programming for the web. As a research practitioner whose academic background is rooted in biophysics and Asian studies, Professor Braun studies the design and visualization of information through applied practice across arts, humanities, social sciences, and natural sciences. His work has used visualization to explore topics ranging from comparisons of how US and Japanese history textbooks talk about the bombings of Hiroshima and Nagasaki, to the cyclical structure of the film The Big Lebowski. These projects have spanned collaborations with many organizations beyond Northeastern, including with Project Information Literacy, Partnering Lab, the Environmental Data and Governance Initiative, and the Lab of Hidenori Watanabe at the University of Tokyo. So we're really excited to have Professor Braun here, and I'll be trying to control to him now so he can share his slides and we get started on the workshop.
Thank you very much for that introduction. Thank you for having me. I'm happy to be here. Again, my name is Stephen. You can call me Stephen. Please feel free to call me by my first name. This is very informal. And as was noted, I spend a lot of time doing work in data visualization and teaching data visualization. So my interest in data visualization actually got started with the natural sciences. My background is originally in biophysics and biochemistry, and that's where I got started being interested in visualizing data beyond the natural sciences alone. So my early research started with visualizing molecular structure of biomolecules, particularly protein structures, and then DNA and RNA molecules. And I got really interested in sort of this idea of taking a data set and communicating that through the help of design. So that's really going to be the focus of this workshop today. I'm going to introduce some key tools that you can add to your toolkits for deconstructing design and using design to communicate data, and also use those tools to improve the quality and effectiveness and clarity of the ways in which you communicate your data. So here's a quick overview of what to expect for these next couple of hours. This schedule is a very approximate schedule. Things will shift around a little bit as we move through the next bit of time here. But we're going to start with some introductions. Then there will be a lecture that will be focused on some basic principles of information design. Following that, there will be a breakout activity where you'll get to critique some examples of visualizations in small groups. Then there will be another lecture based on improving figure clarity through the help of design. Another breakout session where you're asked to discuss how to redesign or improve some example visualizations. And then we'll wrap up at the very end and just sort of encapsulate what we've talked about in today's session. And I'll also give you tools for doing further exploration on your own. Now, I want to situate today's discussion within a larger context. And that larger context is really the entire data pipeline in which we might do work in visualization. So the step of visualization is really just one step in the midst of a longer string or sequence of many different activities. And we all know this to be the case because we're never purely focused on designing a visualization of a data set. We're often very much involved in collecting the data set for that visualization, and then structuring and cleaning it up, analyzing it, preparing it for visualization, and then presenting that to other people, such as through scientific journal articles, in order to share your message and share your data in a broader audience. So I just want to zoom in a little bit on this workflow because there are some important things to note about this workflow that will have implications for our discussion of design. So a common workflow for visualizing data looks something like this. So we start by getting some data, and that could be from a scientific instrument, from your own research. It could be from a data source on the internet, from an app. There are many different places we can get our data. And once we get those data, we realize we can't do anything with them until we clean the data set up in order to make it amenable to analysis. So that could include things like getting rid of empty rows, or standardizing the format in which a particular column of data is written, things like that, or clarifying ambiguities in the structure of a data set. Once we've cleaned up the data sets, we can then analyze it. And in that process of analysis, we get it into a structure that we can then use for generating the visualization. Before we can actually do the visualization, we'll need to export that analyzed version of the data set in order to get that into a format that our visualization tool can then understand. And then finally, we're at that step of being able to actually visualize the data. And through this process, we load the data into a visualization tool. Could be Excel, could be R. There are many different tools for doing this. And then we can actually design the bar chart or the scatter plot or the line charts that we want to make for our presentation or for the journal article that we're trying to submit. Now, the reason I'm showing this pipeline is because it's important to keep this in mind whenever we're thinking about designing a visualization, because the act of visualization itself is not an isolated thing. By the time we get to the end of this pipeline, but by the time we get to this point of visualizing our data have likely transformed significantly from where we started, from way at the beginning of the pipeline when we got the data in the first place. And each of these steps along this pipeline represents sort of us working with a different expression of the same data. So that by the time we get to the visualization, the thing that we call the visualization is really the accumulation of many different design choices. Some of those are explicit and conscious that we deliberately make ourselves. And some of them are implicit and subconscious, and we may not even realize that we're making them in terms of things like how we clean up our data set or how we export that data set in a particular format in order to use it for visualization work in another tool. So in some visualizations, like this one you see on the screen, that accumulation of design choices can be clearly apparent. So we might look at this visualization and laugh a bit because our first sort of gut, but at the same time, this visualization is being very deliberate and very clear in demonstrating to us all the different kinds of design choices that went into creating this figure. Most of the time, the visualizations we create, that accumulation of design choices will be less visible. Again, some of these things will be implicit and subconscious. And that means we have to be much more intentional and deliberate in how we design our figures so that when someone reads or looks at our figures, they don't start questioning specific design choices we make along the way. So that's sort of going to be the focus of our conversation today. We're going to practice deconstructing intuitions around design and then try to reconstruct them again through some key design ideas, concrete design ideas that we can use to improve the quality of a visualization. So we're going to start with a short small group activity. You're going to be placed into breakout rooms. And in those breakout rooms, I'm going to ask you to do a couple of things. So first, in those breakout rooms, I'm going to ask you to briefly introduce yourselves to one another, your name, if you're comfortable doing that, your research. And then after the introductions, I want you to spend some time briefly discussing this figure. And you'll be given a link to a Jamboard that shows this as well, along with these questions. So discuss this figure and discuss whether or not you think this is a good or a bad figure. Very open-ended question. I'm not giving you any definitions of what good or bad means in this case. I want you to sort of reflect on your intuitions, your gut reactions to this, and then try to articulate your gut reaction about good or bad design through references to specific parts of the figure's design. Anything you notice that could be color, scale, use of encodings, use of labels, etc. doesn't matter. I just want you to start deconstructing your intuitions, okay? So I'm gonna stop sharing my screen for a moment here, and we're going to start getting you put into these breakout rooms. And let's spend 9 minutes. So we're going to come back, pull you back at 12:30 to move on to the next part. All right, welcome back. Again, a very short sort of first activity opportunity to introduce yourselves to each other. You'll have more opportunities to look at this figure and talk about it later in the workshop. So if you felt like you didn't have enough time, don't fret. You'll have another opportunity to do so. What I wanted you to do in this first activity was, again, really just focus on your intuitions, what you noticed. Because I'm going to argue that your intuitions are going to be one of your best tools you have for improving the quality of the design of any figure that you make. Those intuitions are going to be guided by the same kinds of principles that you follow in your research. Principles of accessibility, rigor, and clarity, these things that matter a lot in the way that you conduct your research, are going to matter just as much in design. So I'm going to ask us to lean into those intuitions and those principles and sort of figure out how to take those principles and translate them into a visual space. So I'm going to do really a flyby tour of key tools and ideas in design and designing for information. So I'm going to throw a lot of stuff at you, really focus on the big ideas that we sort of pass by, and then you'll have the opportunity to apply those in a small group activity focused around critique. So I'm going to talk about designing for information. And when I talk about that, I'm really working with the working definition you see on the screen. So this is the use of visual encodings to represent information or data in a way that facilitates exploration, discovery, and analysis. And I use this working definition because this points directly back to the thing I talked about with these expressions of data throughout the pipeline of our activities. So in this case, our information, the data, are the raw material we're using for expression. Through visual encodings, we express those through graphical elements. And then we design the overall figure in a way that facilitates exploration. And that's really a reflection of the design of that expression. So we're going to be using this working definition for our discussion today. Now, as we talk about information design principles, we need to establish a common vocabulary for the language of visualization. So I'm going to sort of briefly walk through that now. So a visualization represents measurements, qualities, or characteristics encoded through a data set. And those measurements or qualities could be things like relationships between quantitative variables, comparisons, changes in volume over time. These visualizations can be different varieties. So we all know that there are things called scatter plots, bar charts, and area charts. And they aren't just different because of some special quality intrinsic to them. They're different specifically in how they're constructed. And the way that they're constructed is expressed through these things called visual encodings. So visual encodings are the marks and channels we use to communicate data. Marks are the graphical primitives we use to notate individual observations in our data sets. So for example, in a scatter plot, the mark type is a point. In a bar chart, the mark type is technically a line. And in visualization, there aren't many different kinds of marks. Really, any kind of visualization you make, even though it may look very different from another kind of visualization, you can boil it down, reduce it down to one basic kind of mark type. So those include things like points, lines, areas, containment, and links. So these are the graphical primitives we use to notate individual observations. Now, channels are the other parts of these visual encodings. And a channel is a visual attribute through which we encode data values, such that they can be interpreted by our reader. So for example, in a scatter plot, we said that the mark type is a point. The channels that encode data are position, both X and Y position. And every kind of visualization can use a wide variety and combination of different channels. So these include things like lengths, for a bar chart to encode values for comparison, areas in an area chart. Things like density and counts are intrinsic to the construction of a scatter plot. There are all these different ways that we can encode different data values of different variable types through the use of visualization. So the most basic kinds of visualizations we're most familiar with are really deconstructed across these different dimensions: mark type and channels. So I encourage you to start thinking about visualizations in this way. Every time you see a visualization, don't just think, oh, that's a bar chart, but think, this is a visualization in which data have been encoded through line marks, and those data have been encoded through the channels of horizontal position and length. As you start deconstructing visualizations in this way, that is sort of a good first step to improving the quality of that visualization. So I'm going to argue that designing for information means using design to maximize the expressive potential of the marks and channels that we choose to communicate our data. This is really what information design is all about. Information is encoded through visual encodings. Design is the procedure by which we maximize the ability of other people to understand those encodings. So some key dimensions of expressive potential include composition, color, and typography. So I'm going to provide a very brief overview of these ideas and how they manifest in visualization in general, as well as in scientific visualization in particular. So let's start with composition. When I talk about composition, I'm referring to the visual arrangement of content and its distribution over both space and time. So there are many different kinds of compositional techniques. The ones I'm going to talk about now are the use of white space, alignment and justification, and these things called Gestalt principles that affect how we interpret a visualization. So let's start by talking about this example that's on the screen here. This is an example that I would argue is really well designed. It's well designed in the sense that it's easy to follow the content throughout the figure. There's a lot of stuff packed into this infographic. There are many different kinds of visualizations, but they aren't presented in a way that's overwhelming. And the reason why it's not overwhelming is because the design of this figure really follows a very strict grid structure, and that grid structure leverages the use of white space. So here I've placed gray rectangles on top of all of the main blocks of content, including text content as well as individual visualizations inside the figure. And I want you to notice the white space between the gray rectangles. And I want you to notice how the gaze of your eyes follows the movement across those blocks of content. So here I've drawn in arrows, sort of the way that I sort of interpret this arrangement of information. So when I look at these blocks of content, my eyes follow from left to right, from top to bottom, and that flow is really organic. My eyes don't have to do much extra work to understand what blocks of content are grouped together and what groups are distinct from other groups. And that's achieved through the use of white space. When we look at this figure, we don't first notice the white space. It's subconscious, it's implicit. But that subconscious behavior is critical to being able to understand what this figure is trying to tell us. Here's another example that uses the same kind of idea, but in a slightly different way. So in this visualization here, this is an infographic about the state of global fishing. And like the other example, there's a lot of content packed into this figure, but that content is made and arranged in a way that's digestible. We have these chunks of content of different sizes, but those chunks are related to each other by consistent ratios. And the chunks are organized in a grid layout. And that grid layout helps sort of partition the overall canvas space into understandably sized regions so that we can sort of figure out how to separate one chunk of content from another in this very densely packed visualization. So both of these examples are similar, and they're related in their design. They're related in the sense that they both use grids to organize the content. They differ in that the second example I showed you, the one on the left here, uses an explicit grid that's designed through the use of lines. And the other example, the first one I showed you, uses an implicit grid with the help of white space. So these grid layouts can be extremely powerful for making our content just easier to understand by way of reducing the chance of being overwhelmed or disoriented by where do I start looking in this massively complex visualization that I'm looking at. Now, these techniques of white space, alignment, and grids are very powerful, and they're very easy ways to improve the composition of a figure. And we may not often think about why this works, why these very seemingly simple things are so effective. And the reason they're so effective goes back to these things called Gestalt Principles of Perceptual Organization. So you may have heard of these Gestalt laws in the context of like pure art and pure design. These are sort of psychological principles that are manifested through visual design that explain how human perception tends to group content together in digestible chunks. So there are many different Gestalt principles or Gestalt laws that sort of describe how different kinds of graphic designs work or don't work. In visualization, we're going to really care the most about two principles in particular, and those are the laws of proximity and similarity. The law of proximity says that objects that are close to one another in a figure, in a design, are grouped together as though they are part of the same unit, the same group, the same category. The law of similarity says that objects with like appearances often get grouped together sort of subconsciously by sort of encountering that design. So that could be another kind of grouping based on category in a data set, for example. Now, these principles of proximity and similarity operate at all the overall design of a visualization down to the elementary atomic graphical elements of a visualization. So let's zoom way into that lowest level and see how this manifests there. So in a lot of visualizations, we tend to use things like symbols to indicate different groups of data in a single figure. We're often needing to show data for multiple groups or categories in order to compare and contrast them. Now, in this thing that you see on the slide here, and that's panel that says A, we have sort of an abstract representation of what happens perceptually when we see these different kinds of symbols connected or not connected to each other in different kinds of figures. So in that first cluster of 4 points at the top, we have 2 squares and 2 circle markers. And based on the law of similarity, we might be first inclined to group the squares together as being one category and the circles as belonging to their own separate category. If we draw a line between the square and the circle markers, now that law of similarity, the sort of the priority of that in our perception has been overruled by a law of proximity. And that law of proximity is being created through the use of these lines between the points. In the bottom example, we've actually put an enclosure around 2 points that are not connected by a line. And now there's yet another competing perception and how to organize the groupings of these points in this visualization purely by adding yet another new design element. So this actually happens often in the most basic kinds of visualizations we most commonly make. In panel B here, there is a scatter plot of some sorts, or perhaps a time series, where we have 2 different marker types, squares and circles, but there are no lines between like markers. So based on Gestalt principles, our first sort of gut intuition might be to group points together based on proximity. That would group together some circle markers with some square markers. But if we provide further assistance in the design of this visualization through very simple things like drawing lines between similar marker types, or drawing a circle around a cluster of marker types of different markers, we sort of give more information to the reader that helps them understand what we should be paying attention to in this visualization. So again, a very simple kind of visualization that we make all the time, but we can deconstruct it down to these elementary design principles. And again, if we can deconstruct all the way down, we can reconstruct and rebuild to improve the quality of our designs. So composition can be created through a lot of different techniques in the design of a visualization. A common thing that we need to do in scientific visualization in particular is to create composition through the use of perspective. So for example, we often need to represent or visualize data that are distributed across more than 2 dimensions. Now, for the most part, 3-dimensional visualizations are very challenging and very tricky to use. And they're very tricky to design effectively. And the reason for that is because perspective visualizations are very easily susceptible to perceptual aberrations, meaning people will not be able to accurately compare or interpret the data encoded within those visualizations. So here's an example of a figure from an article in The Atlantic from many years ago. This is a visualization that's showing competing types of visualizations on 2 different perceptual axes, perspective axes, about changes in number of classified documents over time. And the problem with this visualization is that maybe it's interesting or provocative to look at, but as soon as you start trying to interpret what data it encodes, it falls apart because you're not really able to accurately interpret what a given stack of papers represents in terms of a numeric value, and then cross-reference that with the other perspective plane that's oriented 90 degrees from the main vertical axis. So we have these competing axes of perception that make accurate comparison practically impossible. So doing things like taking this weird stack of papers, which is supposed to be like a bar chart, and trying to map that to the vertical axes way on the left of the figure is problematic unless we get a ruler out and draw a line between the stack of papers and the axis itself. So as a general rule, don't use perspective to visualize 3-dimensional data unless your data are inherently 3-dimensional. In other words, unless you're working with spatial data. So sometimes this does have to happen, right? We have things like molecular data. We want to visualize the structure of a biomolecule. Like in those cases, there's no way around using perspective visualization to represent that structure. So when we do have to do that, we can really rely on some key perspective techniques to communicate what we want to communicate. So in this example here, we have things like partial occlusion, making certain geometries appear distance in space. That can be amplified through differences in size to indicate perspective. Same thing with difference in shading. And for the most part, when we see visualizations like this, these kinds of techniques are very effective. Because in these kinds of visualizations, we care less about being able to precisely interpret what kind of data each individual piece encodes, and we're more interested in global things like the overall structure and what that structure means for the function of the molecule. We get into more trouble when we take more abstract data that don't intrinsically have 3 dimensions and then try to map them to a 3-dimensional visualization. So in this example here, that panel in B, that is a flat 2-dimensional representation, a heat map representation of an abstract imaginary data set. And in panel A, we've tried to turn that into a 3-dimensional visualization by taking the value of each cell and mapping that to the height of a bar. And because of perceptual aberrations, our difficulty in perceiving perspective, there ends up being a lot of discrepancies between an apparent height and thus apparent values when trying to compare individual bars in the visualization. So again, don't use perspective in visualization unless you know what you're doing and unless you have to use perspective because your data are inherently spatial in nature. Now, the next thing I want to talk about is color. And this is hugely important because this is the thing that we all think we understand, but actually all know nothing about. And this is the part of visualization design where we often get tripped up the most, often in places where we don't even realize it. So color is one of the most important and sort of noticeable dimensions through which we can encode information, but it's also the dimension that's used most inappropriately. And the reason for that is because of differences between how we as humans perceive color and how the machines that design our visualizations perceive color. So humans perceive color based on hue, saturation, and lightness. There are other models that explain human color perception. I'm going to focus on HSL. So by hue, I mean the color name, red, green, blue. By saturation, I mean the magnitude of that color, the quantity of that color. And by lightness, I mean the quantity of white in that color. Now, computers don't perceive colors in hue, saturation, lightness. Fundamentally, computers perceive color in quantity of red, green, and blue. Now, the reason why this matters is because being able to encode color in quantities of red, green, and blue means that machines are good at perceiving colors in perceptually uniform steps. So in that top bar there, this monochrome gradients, I could find any two equally spaced slices of this color gradients, and they would represent equal steps or changes in color value. Humans are terrible at perceiving colors in uniform steps. So for example, here I have the rainbow color palettes, and you might notice in particular that in these transition regions between the blue and the green, and then the green and the red, there are these very bright regions of blue or tealish color, and then very bright yellow. And you might notice these things because as humans, for example, our eyes are very good at noticing the color yellow because of the way that our eyes are made. So the problem with this is that as we get closer to that yellow region, every step in change in color gets bigger and bigger compared to these sort of internal regions where those steps in color are smaller. So this is important because if we start mapping data values to color palettes that are intrinsically non-uniform in how we perceive them, then we can't assume that a color palette that builds into itself uniform steps in data will be interpreted by our readers as also being uniform steps in data. So this often has big consequences for the design of our visualizations. So all this means that when we design a visualization, we need to really spend a little bit more time than we're comfortable with thinking about color. And thinking about color is not something that has to be super complicated. It really just means taking a step back and making sure that the color palette that we choose does its work of bringing unity, identity, consistency, and hierarchy to a visualization. So I have 4 quick tips for choosing a quote unquote good color palette. And by good, I mean effective in what it's trying to communicate and its purpose. So my first tip is to use colors that are easy to distinguish. This might seem obvious, but we violate this rule all the time in visualization. So on this slide at the top, you see a 4 color palettes, 4 colors interpolated between green and this light or pale yellow. And for the most part, these 4 colors are relatively easy to distinguish side by side. So we could use them in a visualization and be able to articulate which points are which color in this palette. Now, when we take a small distinguishable color palette like this and interpolate it to a palette of 10 colors, it becomes much more difficult to differentiate adjacent colors. So we've decreased the sort of change in color between individual steps. And whenever we decrease that size and step, it becomes much more difficult for us to interpret differences between data points encoded through color. So again, we do this all the time, often because we think we have so much data and we need to encode it through color that we sort of just set aside this rule of distinguishability in favor of being able to communicate the data we want to include in our figure. So here's an example of a figure that does just that. There's a lot going on in this figure. It's very disorienting, not only by way of the number of lines, but also by way of the number of colors. So the color palette at the bottom, there are just way too many colors here. So it makes it very difficult to read and sort of figure out how we're supposed to interpret anything that's going on in this figure. So when choosing colors that are easy to distinguish, it's really best to use a limited number of different colors. And really 4 to 6 different colors is ideal, no more than 12. If you have too many colors, try to transform your data to reduce the total number of data classes to limit the number of different colors you do have to use. My second tip is to use colors that are accessible. So this means a lot of different things. I'm going to start by talking about accessibility when it comes to color blindness. So with a color palette, a rainbow color palette that's perceived in complete or full color vision, someone who has vision deficiencies in their ability to perceive color will not see those differences in the same way that full color vision is capable of doing that. So those differences get flattened in really any form of color blindness. So for example, if we look at this green and orange pair in the full color palette, that gets flattened into this sort of the same hue, but different lightnesses. And that's completely just flattened our ability to distinguish those two different classes of data if we're using this to encode categorical data, for example. Now, this doesn't only apply to issues of color blindness, it also applies to issues of like technical accessibility. So for example, when we can only print something in grayscale, colors are lost entirely. So if we're using color as a significant encoding for a figure, and we expect someone to go print out that figure or the paper in which it's located on a black and white printer, because I don't want to waste color ink, then they won't even see those encodings in the first place. And the whole point of your visualization may have been completely lost purely by way of a technical choice on behalf of the user. So as a general rule, we should really focus on limiting our use of colors. And when we do select colors for a visualization, we should consider the effects of color blindness, as well as the effects of technical restrictions on how people might be looking at our figures. Now, it's also important to remember that under the best of circumstances, even if we assume everyone has perfect color vision, we still have to worry about accessibility. Colors. This is a choropleth map of the United States where counties are colored to indicate a certain value in a data set. And I have intentionally left out the color legend for this figure. So as I sort of keep this color legend out, I might ask you, okay, just by looking at this visualization, what's one big thing that you notice? And that one big thing you notice might be there appears to be a sharp divide in values between East and West. And that sharp divide, that apparent sharp divide, is coming from the choice of color palettes in the design of this visualization. Now, if I put the color palette back in the color legend, we can see that every step in color actually encodes an equally sized step in a data value. So in particular, in this important transition region in human perception, from green to yellow, we have equal steps in data values, but we don't have equal steps in color perception. And so our intention of using color to encode a data set has actually fallen apart, because in practice, the thing that we're encoding cannot be accurately interpreted by the reader without the reader having to do extra work to override their natural way of perceiving colors and how it's being used in the figure. So when we have to use color, we should use these perceptually uniform color palettes. You may be wondering, where do I find a perceptually uniform color palette? Qualitative color palettes. Now, these use different hues to indicate different classes of data. And these are good for categorical and nominal data. Now, the reason I bring this up is because sometimes we choose because of how they function in our visualization with respect to the kinds of data that we are visualizing. So in sequential and divergent color palettes, we should be using those primarily for numerical data. And every step in color should encode an equal step in data change. Qualitative color schemes should only show contrast between classes for nominal data and not order of magnitude, such as with ordinal data. The reason I bring this up is because a common mistake is to use a qualitative color palette that has changes of lightness inside of it to encode what is actually a nominal variable. So here I have 3 examples of color palettes that might be built into a visualization tool. And we might use one of these qualitative color palettes that looks like this to encode that nominal variable. Now, in a palette like the one you see on the screen here, we have 10 different hues, which we could use for nominal variable values, but each hue has 2 different lightness values. The reason why this is important to notice is that because of these differences in lightness, there is a real risk of the reader unintentionally grouping together nominal values as being part of the same ranked group. So for example, if 2 different nominal values are encoded with these 2 different lightnesses of blue, the dark blue points and the light blue points might be grouped together in our perception, even though they have no grouping relationship whatsoever in our original data. In something like this, that effect is exaggerated even further. Here we have 5 different hues, but each hue has 4 different lightness values. So this would be a terrible color palette to use for nominal data, because what will likely happen is that if we have more than 5 different nominal values, we're going to start recycling these different hues and start getting multiple shades of some hues, but only single shades of other hues. And this can turn into a mess when it comes to clarifying what color's encoding in our visualization. So the last thing I'm going to say about color is to use colors that minimize perceptual interactions. So colors interact with each other all the time in our perception. These interactions are demonstrated through optical illusions. So there are optical illusions like simultaneous contrast and contrast of hue that affect our ability to accurately perceive colors. So in simultaneous contrast, the example you see there, that middle purple bar in front of that gradient background, that's the same hue all the way through that middle bar. But because of the surrounding colors, the context in which it's presented, it looks like that middle color is changing in value from one side to the other of that bar. So color interactions like these, you may not think happen in visualizations. They happen all the time, in particular in heat maps. Heat maps are a very popular visualization in scientific communication. We don't realize that sometimes our heat maps and the way that we've designed color into them are actually diluting our ability to clearly communicate our data. So here's an extreme example. Here we have a heat map where there's a divergent color palette. The divergent color palette is quite extreme in its distribution of colors, right? We have a lot of reds and oranges on one side of the spectrum and only a few blues on the other side. So this extreme distribution of colors means that when we look at this heat map, the reds and the yellows pop out a lot in our perception. Because again, as humans, we notice yellow. We notice brightness very, very easily and much more quickly than we notice darkness. So these cells pop out significantly, and we may not want that to happen. Maybe we don't want these cells to sort of infer a more significant difference in data than actually exists in the data we're trying to communicate. Here are a couple less extreme examples. Again, two more heat maps. The one on the left shows color differences based on saturation against a black background. And those differences are a little bit more difficult to perceive than the color differences in the right example, where the color differences are based on lightness against a white background. Humans are, again, very good at perceiving very subtle differences in lightness, not so good at noticing subtle differences in darkness. So a very simple thing you can do to improve the use of color in a heat map is don't use a black background or don't use black as sort of your zero middle point. Use white, and that will instantly improve the readability of your visualization. Now, within figures, we can see the effects of simultaneous contrast and may not even notice it. So for example, in this slice of a heat map here, there are two cells that have asterisks in them. If we look at them, it might appear as though they are different colors and thus represent different values. In fact, they are the exact same value. They're the exact same color value. The effect that we see here, this apparent difference, is the result of simultaneous contrast, this optical illusion where our perception of a color is modulated and manipulated by the colors surrounding it. So all that to say, just be very careful and be very selective in how you use color in visualizations. You may think it's a very quick and easy way to improve the intrigue or the effectiveness or the clarity of your visualization, but sometimes it can actually decrease that clarity for reasons that you may not even be immediately aware of. So here are a couple of quick examples where I think color is used very effectively. And I think they're being used effectively because the point of the color as an encoding is really to point attention, not necessarily to encode individual values, but to tell the reader, pay attention to this thing, pay attention to this trend I'm trying to show through this figure. So in this particular visualization here, we have color that indicates different groups, thresholds of the data. And this is a very effective use of color because most of the figure, most of the points in the figure are this sort of light gray color that we don't need to pay much attention to. But what's more interesting and important to pay attention to are these higher values, sort of more vertically up on the vertical axis. And the person who designed this visualization is really grabbing your attention towards those higher values by using this thresholded color palettes. So a good example of using visualization to really pull out a narrative as opposed to encode individual values. Same thing here. Again, here we have an example of color to pull out a strong narrative. This is a visualization looking at the length and average hotness of summers in Tokyo. And this is a heat map. And one of the first things that jumps out to you when you look at this visualization is there's this growing pool of red towards the bottom and in the middle of this visualization. So here the color is being used to encode individual values, but more importantly than the individual values, the color here is really grabbing our attention to the overall trend that is being communicated through this visualization. I mentioned quickly this tool called Color Brewer. The link to this is right here. This is a tool that gives you a list of perceptually uniform color palettes. Originally designed for cartography. You don't have to use it just for cartography, for designing maps. I use it for every visualization that I create. So you can find lots of different kinds of sequential, diverging, and qualitative color palettes. You can find color palettes that are colorblind safe, photocopy safe, print friendly. So if you ever have the opportunity to choose a custom color palette for a visualization, this is a good sort of first stop for doing that. Now, the last thing I'm going to talk about very quickly is typography, because typography is the other thing we know nothing about, just like color. So I have a few basic rules here to follow. Really, we could spend an entire workshop talking about typography, just like with color. But some key things to keep in mind when putting text in figures are these things here. So first, don't mix and match typefaces unless you really know what you're doing. Stick to a single type, serif or sans serif, for all text and focus on variation through size and weight. And lastly, remember that typography is integral to composition and not separate from it. It's not an afterthought. If you're going to include text in your figure, start thinking about it from the very beginning of your design process. When I say typeface, I'm referring to things like Arial, Baskerville, Helvetica, the names of fonts that we use when we create Word documents on our computers. Now, the word typeface and font, they are different words. We use them interchangeably. They mean different things. I'm going to focus on the word typeface to refer to the name of the type in which we're writing our text. So there are two key classes of typefaces to really care about in information design. Those are serif fonts and sans serif fonts. A serif font has these little feet at the ends of these lines. A sans serif font doesn't have these little feet. And these different kinds of fonts are better or worse in different kinds of reading situations, depending on if you're doing long form reading or short form reading, if you're working with print materials or digital media. These different kinds of typefaces actually have significant consequences for legibility across different media of visualizations. Now, when we use typography in a visualization, it's really best to use it simply, but also not only use it simply, but also consistently. So by this, I mean, use typography to build hierarchy into a figure, into a visualization that guides where the reader's eyes should go in that visualization, and do that through the manipulation of simple things like weight, color, and size. So here's an example of some text without any typographic hierarchy. All the text looks exactly the same. Here we've modulated things like color, font weight, size, style in terms of italics, and even just these simple manipulations go a long way in improving the readability of this figure. Because now we can scan this text and find the information that we want to find without having to read everything and figure out what we're looking for. Here's an example of a figure that uses typography in a very simple way, but very effectively. So here there's a single typeface that's used throughout the entire figure. That typeface is a sans serif font. But even though there's a single typeface, there are clear distinctions in weight and size. And those clear distinctions in conjunction with compositional techniques like white space and grids makes it easy to read the content in the order it's intended to be read. So simple doesn't mean ineffective. Simple can often mean extremely effective depending on how you use it in the design. Whenever you're working with type, remember that readers will notice inconsistencies everywhere. Every single character in your text, as well as every single space or tab or change in alignments, will be something that is noticed even subconsciously by the reader. So doing things like taking a step back and looking at the overall topology of your text can be a helpful exercise. Because, for example, in the figure you see here, in panel A, there's some text with excess spacing, like carriage returns, places where additional spacing between bullet points and text would be more helpful to sort of provide a more consistent structure to the text. If we look at that reddish line, that brownish line on the right-hand side, we have sort of this very jagged edge along the right side of the text. And if we just clean that up a little bit with the stuff on the right by making the carriage returns and number of spaces more consistent across the text and aligning that text on the right-hand side to sort of clean up that right-hand edge of the text, it makes it easier to read the content. And easier to read means a lower likelihood of being discouraged. And we don't want to discourage our readers when we're trying to tell them something important about our data. So these things operate at many different levels in the visualization. Things as simple as aligning annotations and callouts in a figure can also go a very, very long way. And these are things that, again, are very simple fixes. They're just things we don't often think about. And as we start thinking about them, that's sort of our first step to improving the quality of our figures. So all of these things, again, a flyby tour of composition, color, and typography, they're just a starting point. But they are concrete design elements through which we can start to critique the effectiveness of any visualization that we design or that we see in designed by somebody else. So being able to deconstruct these intuitions of, oh, that's bad, or oh, that's really nice, will give us sort of a better sense of, okay, what do I notice about what's bad or what's really nice, and how can I use that to improve my own design practice in the figures that I make. So with all of that said, I want to give you an opportunity to discuss these things in small group with some actual examples. And we're going to do this in a very quick, sort of very simple kind of critique. So we're going to break out into small groups again, like before, and you have your Jamboards now, so you'll find resources in the materials for this on those Jamboards. And I'm going to give you a bunch of examples of visualizations. I'm going to ask you to critique one or two of those visualizations. You can pick and choose which ones you want to focus on, doesn't matter. There are many options there. So as you discuss some questions, some critique questions around your chosen visualizations, there are certain rules you need to follow in order to make the critique rigorous. So those include things like using a neutral voice. You can't just criticize a visualization and every statement you make shouldn't just be an opinion. You should have a clear justification for why you feel or think that way. And as you provide criticisms, as you critique the thing you're looking at, offer solutions. Offer alternative ways of designing the thing that you think could be done better, and discuss why you think that would make that visualization or that part of the visualization a little bit better. Okay? So these are the questions I'll ask you to discuss in your groups.